Thank you very much. Our next speaker is Jessie Pontigo Herrera. He made his bachelor thesis in la Universidad Autónoma de Herrera, and his master's degree she made it here in UNAM, and his PhD thesis she made in a mixed status among with about Madrid at the University of Dijon, Bourbon in Dijon, and here in Mexico City. Thank you very much.
Well, first of all, I want to thank Laura for making this event possible, and I want to thank you also for being part of it. So the title of my lecture is Noetherianity and length of iterated integrals in Poincaré-Pontryagin functions. So it is a little related with what Musigno talked about, and I'm glad that he already introduced some of the concepts I will use. But if you got lost, you can now catch up because I will repeat a little bit of what he talked about. So the first part, to give a little bit of context, it is related with limit cycles. And in a way that we will start with, I will start the real setting. Later I will pass to the complex. And we will start with a real polynomial. And this is the question of perturbation of Hamiltonian equations. So I will start with this Hamiltonian equation defined by this Hamiltonian f. And we will assume at the beginning that we have an identical cycle that is a continuous family of periodic orbits. But then we will perform a perturbation, a polynomial perturbation here. P and Q polynomial. And epsilon is just a small parameter. And we want to understand what happens with this continuous family after this perturbation. It is somehow related also for those who were here the first week with one of the lectures that Ilyashenko gave us. So after this perturbation, some of these periodic orbits can remain as periodic orbits, but generically most of them will be broken. And in order to study this effect, one considers the first return map. So we consider a transversal here in this neighborhood, which remains as a transversal here. Here I'm with epsilon different from 0, and this is the case epsilon equal to 0, which is the Hamiltonian equation. And the first return map, also technical detail and some notation, we will consider this transversal parametrized by the values of f. This is possible because in this neighborhood we only have regular points. And I will denote, for instance, this oval gamma T0, which means that it is inside the level T0 of f. And f with this parameterization also it means that f restricted to this transversal is the identity. Okay, so it means if this point here is T0, and if this point is T, it means this oval is gamma of T, which is in the level T of f. Okay? And now with this Poincaré first return map, one considers, for instance here, I start with the point T, and I take the first return to this transversal, and I will denote it with P epsilon gamma, which gamma is this family of continuous ovals of T. And this is an analytic function, so we can express it as a power series. And since we start with the Hamiltonian when epsilon is equal to 0, we have, it starts also with identity plus some analytic functions. Plus higher order terms. And those functions here, they are called the Poincaré-Pontryagin functions. In the literature of this kind of problems, you can also find the name of Melnikov functions, but I learned last week that actually it was Poincaré and Pontryagin, the first person that studied them. Also, we sometimes may use the so-called displacement function, which is the difference between the first return map and the identity. So I will write it here. This is displacement map. And it means that it is also given by this power series in terms of this Poincaré-Pontryagin functions. Okay, so since we want to study what happened with this oval after perturbation, we have two possibilities. Since they are analytic functions, the periodic orbit that remains as periodic orbit after this perturbation are given either by the fixed point of the first return map or by the zeros of the displacement map, which is an analytic function. It means that they are isolated zeros, and they correspond to isolated periodic orbit here. So they correspond to limit cycles. So if we want to bound the limit cycles, we can start with bounding the number of zeros of this displacement map. And okay, so either we have that this displacement map is not identically zero, or it has isolated zero. So we have two alternatives. I will write it here. Okay. So we have two alternatives. The alternative A is either this function, this displacement map is not identically zero. It means that there exists a first non-zero Poincaré-Pontryagin function. I will call it I mu. This is not identically zero, and therefore this displacement map starts with the order mu in epsilon plus high order terms that I will denote using O of epsilon mu plus 1. And in a similar way as Irashenko showed us for the case mu equal to 1, it turns out here that the number of zeros of the displacement map is zeros. is bounded locally by the number of zeros of the first non-zero Poincare-Pontryagin function. Okay, this is the first alternative. And the second one that can happen topologically over there is that this displacement map is identically zero, which is related to the fact that all of the Melnikov functions vanish identically. Okay? And in this case, it means topologically that after the perturbation of all of the periodic orbits remains as periodic orbits. And we say that we preserve the center. The first case is also called as the infinitesimal version of Hilbert sixteenth problem. Which is the problem of giving an upper bound for the number of limit cycles that appear after this kind of perturbation. And the second one is related with the infinitesimal version of Poincare center focus problem. Where the classical problem of center focus is to provide conditions for a planar polynomial equation in order to have a center singularity. As Ilashenko told us this morning, there is a special case when you have this kind of singularity, these centers ones. They are not the hyperbolic. So they are a special case, and it's not easy to know. You have some nonlinear terms, but a linear center is not straightforward that after nonlinear terms, you will remain with a center singularity. So it's a special case. Okay. And now, what I want to stress here is that these Poincare-Pontryagin functions, they keep essential information to decide in which case you are. Either you have a center focus problem or you have a bound for the number of limit cycles appearing. So the second part of my talk is to focus on those functions and to try to study them. Okay, so second part is to study these Poincare-Pontryagin functions. So we will start with the order one. So in order one, we have a Poincare-Pontryagin theorem. Which says that the first order Poincare-Pontryagin function, also I will pass to the Papian notation in order to simplify some computations. So instead of working with this differential equation, we will, for simplicity, work with the Papian form, where omega is defined from this perturbation, the P dy minus Q dx. So I will change to this notation. This is equivalent. So with this notation, this first order Poincare-Pontryagin function is just an abelian integral, which was already defined by Monsignor talk, an abelian integral. And I think, well, I can give a sketch of the proof. It's not so difficult. I will use it in the higher order, so I think it's a good idea to, let me add here. Let's denote this arc with gamma epsilon t, where gamma epsilon t goes to gamma t when epsilon goes to 0. Okay, this is the arc connecting the point t with the first return map. So if we integrate df along this arc by calculus fundamental theorem, we have that this is f evaluated at the end points. Okay, but since by the parametrization of this transversal, this is just identity, so this is equal to p gamma of t minus t, which is this displacement map in one hand. And in the other hand, we can write here, we could add epsilon omega and minus epsilon omega, and we integrate again along this arc, epsilon t. But since this arc is tangent to the foliation defined by this form, this integral will vanish, and we end up with this integral. So we had here this power series. Then if you take the derivative in this expression, the first order derivative, of the displacement map with respect to epsilon in epsilon equal to 0, this will coincide with this integral when epsilon goes to 0, which means to the oval at the level t of f, and we get what we wanted. Okay? So the first order Markovnikov function is well known, but what happens if this function, the first order, is already identically 0? In that case, one needs to compute the second order Poincare-Pontryagin. So what happens if this is identically 0? Then in order to have our upper bound of limit cycles, we need to compute the second order Poincare-Pontryagin function. So in order to compute it, let's have a look to this property. As we know, this is already an abelian integral along this oval. And it turns out that this is identically 0 if and only if, I will call it asterisk, it's local result. There exists G and R analytic and I will call this annulus neighborhood U. They are analytic in U, which is foliated by these ovals, and such that omega is written in this expression. And this expression is called relatively exact. Relatively exact form, okay? Well, if we have this expression, now let's think about what happened in this case. I will call it G1 R1. And then to compute I2 of gamma, I propose to multiply this factor 1 minus epsilon G1 by df plus epsilon omega. And you can verify this is equal to the differential of f plus epsilon R1 minus epsilon square G1 omega. Okay? And if you integrate this along this arc gamma epsilon t, then you have df along this arc plus epsilon dr1 also along this arc minus epsilon square G1 omega along this arc. But as we saw in the demonstration of the Poincaré-Pontryagin theorem, this is already the displacement map. This part you can verify. This is of order higher than 2. It is order in order epsilon cube. So if we are under the assumption that I1 is identically 0, it means that this displacement map is given by, it starts on the second order function. And again, you can take the second derivative of the displacement map in epsilon equal to 0 to verify that then the second order Poincaré-Pontryagin function is given by this integral, a positive G1 omega along the oval gamma of t. Okay? So we already know who I2 is.
Can you say again why the PR is order square?
This one? I didn't explain why. You can expand, no, you can use the Taylor expansion of R1 and you can verify it. It's just computation. Somehow it is because using this Taylor expression, you have that this, the integral of the R1 has the same order as the displacement map. So it starts in cube. You have the cube by multiplying again by epsilon. Okay, but it's just computation. Okay. Well, so I will compute. I will say who I3 is. So now assume that you have these two functions equal identically 0, and now you want to compute I3. You follow a similar strategy. Now you multiply your deformation by this expression. And you can verify, you get differential of f plus epsilon R1. I didn't say who was this guy. So by asterisk, you have two equations here. First one was given by I1, which is omega, is G1 df G1 df plus dr1. And you also have that G1 omega. You apply again this expression asterisk, which is over there, and you get this function also locally analytic in U, such that this form can be written as a relatively exact form. So once you have these two expressions, you multiply this part by this, and you get differential of f plus epsilon r1 minus epsilon square r2. And this design alternates, and you have plus epsilon cube g2 omega. And again, if you integrate along this cycle, this arc, you get that, again, here is displacement map. dr1 and dr2, these both are of order higher than 3, this is epsilon to the power 4. This displacement map is already starting in epsilon cube plus high order terms, and you compare. Now you have here plus epsilon cube of g2 omega along this arc, and again, taking this third order derivative, then you get that I3 now is given by minus the integral of g2 omega along the oval gamma of t. Okay? And we have some general expression now. This is called the Francois algorithm. This is point 3 of my talk, Francois algorithm. Which says that if you have I1 equal to I2 of gamma until k minus 1, if all of them vanish identically, then by this local property asterisk, you have a sequence of equations with some analytic functions such that then the first non-zero Melnikov function, ik, is given by minus 1 to the power k of the integral along this oval of g k minus 1 times omega. So we already know who those Poincaré-Pontryagin equations are. But we can go deeper and to look for some structure to identify more precisely who these guys are. So I will make a note. Consider the first equation, g1 ds plus dr1, and take the exterior derivative. Then you get the derivative of g1, which df, and the note omega prime, this quotient, It's also notation. And this is defined as the derivative of G1. This is called the Gelfand-Leray derivative. Which is a kind of the derivation with respect to the differential of f. And in some sense, it is like measuring the effect of the form outside the fibration defined by f. So, and it can be proved that this derivative, this function omega prime, always exists in regular fibers, and it is unique up to some multiple of df. Okay? And so if we already know that the differential of G1 is just this Gelfand-Leray derivative, then we can define G1 by integration of this derivative along paths on the fibers of F. And again, we can repeat the same for G2. G2 can be also given, well, the Gelfand-Leray derivative of G1 omega, it is given by this differential of G2 by the same reasoning. So again, we can define G2 also as the function defined by integration of this Gelfand-Leray derivative. And now I can use this definition instead of the first one that we got in this Francois algorithm. It means that now, using this notation, I1 is already abelian integral, nothing to do about. But I2 can be now written, instead of gamma of G1, I can write this integral. So it is this function defined by integration times omega along this oval. And for I3, we can also shift to this notation, and we have the integral along this oval. I3 was even there. So it is G2 is this integral. So it's G1 omega prime times omega, but G1 was already defined by integration. So I3 is the integral along this oval of the integral with another integral inside times omega. And this is, this kind of expression are called iterated integrals. Let's say what we get from Francois' algorithm is that Ij of gamma is an iterated integral of length, which is the number of integrals that you can find in the expression of length at most j. Okay. I try to be a little bit more precise about this definition here. Okay. So these iterated integrals, they were defined by quería blanco. Aquí había. Aquí tengo. Bueno. Gracias. Okay. So these iterated integrals. More in general, there are these kind of expressions. You have holomorphic forms in a surface, and you integrate along a path with an initial point, and they are just nested integrals. Suppose L is a path parameterized from 0 to 1 to some surface. This is general definition, and it is the similar idea there. You integrate with the first form, you define a function by integration. You can consider actually the pullback, dt1, 2. The function you get, you multiply by this pullback of eta 2, and you integrate and you get another function, and so on, until eta k. Okay, and what is the important aspect about these functions? So, as I said, they were defined by this Chinese mathematician, could say Shen, in the 70s. And he wanted to make a bridge between analysis and topology in such a way that, well, he developed some kind of homotopy, the RAM theory. In analogous way to classical the RAM theory, which is associate a dual element to any cycle in homology. So, and here for Shen, he's working with commutators of he's working with the first fundamental group of the surface with some initial point. And he considered this lower center series. L1 is a fundamental group. And he shows that dual elements of these commutators, we can take this filtration and consider the quotient of commutators of length j divided by commutators of length j plus 1. If you take the dual of this vector space, this is generated by iterated integrals of length j, exactly j. What is the length of the iterated integral? You can define a function with this expression, and the smallest expression gives you the length. So you can also verify that this is an integral of this length if you can find a commutator such that when you integrate, you get not 0. For example, for iterated integrals of length 1, those are just the abelian integrals, and they always vanish along commutators. They cannot detect that topology. But this topology plays an important role in this theory of perturbations in the following sense. There exist some bounds, 5, explicit in the case for first order, it was given by Gal-Binjamini. Dmitry Novikov, Sergei Yakovenko. They gave an upper bound for zeros of the abelian integral. But was non-optimal bound, too big. But anyway, it was an explicit bound in terms of the degree of f and omega. But depending the degree of f and degree of omega. This was given in 2010. 1 year later, another bound was given for higher order Poincare-Pontryagin functions, and this was given by Benditkis, Novikov in 2011. And they gave also an upper bound for zeros of higher order Poincare-Pontryagin functions. But this was depending also on the length of this Poincare-Pontryagin function as iterated integral. So somehow this this length of iteration of the integral is related with the appearing of limit cycles in this perturbation. So we decided to study the nature of this length, how it is related with the Hamiltonian and with the cycle. And well, as was already said in this Musinho's talk, there is something that is called the orbit under monodromy, and it is related in this story. So here I will pass to complexification. Actually, I was hiding this information in those along this talk. I was already thinking in this of this complexification, but I will make it more explicit here. So we have, even though this f it was a real polynomial, we can think of it as a complex function going from C2 to C. And I will repeat a little bit. We have here, if we denote sigma f of f critical values of f, then we get by Milnor fibration that C2 minus this level curve associated to critical values. This was already topologically trivial, locally topological trivial fibration. That allows to make this continuation of the fibers. Here we can have, for some critical regular values, some Riemann surface punctured, and we can go around some critical levels. And you can check what happened with some cycle here. It starts to get a deformation, and such that when you end this transportation of the fiber, you can get a new cycle here. And this is what we call the orbit under monodromy. And okay, with this, I think I have all the elements I need for the statement of the theorem. I'll write it. I think I need a new blackboard. So we the theorem is the following. It is a theorem with Pavao-Mardesic, Dmitry Novikov, Laura Ortiz, and me. We just proved it. I think we finished the proof just last week. So I was ready to give the lecture today. So it was just proved. Actually, we have 2 different or 3 different proofs, but so actually we start already in the statement of the proof of the theorem with the polynomial, complex polynomial. In gamma, you don't need actually real oval. You can take just a loop. In the fundamental group of some regular fiber, which since we are in the complexification, is the Riemann surface with some fixed base point. And then for any natural K, there exists a natural number n depending only on the Hamiltonian on the cycle, more precisely depending on the orbit on the monodromy of the cycle, and depending on this number k, such that if the first n Poincare-Pontryagin functions vanish, then the next Poincare-Pontryagin functions are an iterated integral of length, this technical aspect here, of orbit length at most j minus k. So before, from Francois' algorithm, we had that this could be an iterated integral of length j, but we have improved it, and also this is not only for the first non-zero, this is for all of them after the vanishing of the first n Mendicott functions, j plus bigger or equal to n plus 1.
What is k?
K is any natural number. You pick it in just that to decrease the length in this way, any natural number. And this orbit length, it means that in some sense related to Chen's theory, this iterated integral vanish in commutators of the orbit. I will put here L, with L bigger than g plus 1, but only for commutators in the orbit. It's a little bit not so general that in the Chen's sense, but since we are only working on the orbit, it makes sense. And I don't know how much time I have. 5 minutes. So I will give a sketch of the proof. Which is related also with some name which was in the title, this Noetherianity, how it is involved in this story. So the idea or the idea of the proof. So there are some key elements here. So differential algebras and a theorem in differential algebras proved by written Roundenbush. This was given in the 50s. And this theorem says that infinitely generated differential algebras finitely differential algebra. You have some neutrality property in the way that ascending chains of radical differential ideas stabilizes. So with this idea, we can apply it in our situation as follows. Okay. Let me see if I have enough space. Yes. I will use this table to organize the information. Here I will put a commutator of length 1, which is homology, commutator of length 2, commutator of length 3, and commutator of length 4, etc. And here I will put the order of the Poincare-Pontryagin function. This is first order, second order, third order, and so on. And we consider this Poincare-Pontryagin function on those cycles. So I have the restriction to O1, the restriction to O2, the restriction of I3 to O3, restriction of I4 to O4. Since they are of length at most, they order. This is an abelian integral. Here we have zeros because of the length. And here also I take this restriction. O4 to O3, etc. But the idea is, with these functions, we can define some ideals. I take this diagonal generated by these functions. And I will call this diagonal D1. And if we have a differential algebra finitely generated such that we can define here a differential ideal, then we can apply this Roundenbush to some radical ideal, chain of radical ideals generated by these elements, adding these elements. So at the end, if we get this differential algebra, then we have finitely many generators such that if they vanish, then all this diagonal will vanish as well. And this diagonal vanishes, then it means that you have improved the length for all of the remaining Poincare-Pontryagin integrals. So we are working with diagonals. If I get this diagonal identically 0, I go to the next one and repeat. So the idea, the main idea is to get these differential algebras, but this is also a theorem of a structure that we prove related to that one, theorem of a structure, that provide these algebras. I will put part of the statement. So if you restrict some Poincare-Pontryagin functions to these commutators, then this can be given by a polynomial, differential polynomial, in some basic elements, some Poincare-Pontryagin functions where these are the generators of the homology of the regular fiber. So you work with they could be a basis of vanishing cycles, if you want. Okay. For example, in the case, I just went with this example. The second order along this one commutator of the order 2, let's say delta 1, delta 2. This Poincare-Pontryagin function along this commutator, using the expression given by François' algorithm, we know that this is given by this integral omega prime omega along this commutator. But by properties of iterated integral, this is given by a determinant of omega prime, but actually this prime can go outside the integral by properties of the Gelfand-Leray derivative. In the second row, we have integral of omega prime of delta 2. Here we have integral of omega 1 and integral along delta 2 of omega. And this is a differential polynomial in terms of these basic elements. And actually, this phenomenon happens for all of the elements in the diagonal. That is, if you take the Poincare-Pontryagin function of order j along a commutator of order j, then you get this expression by Wronskians, and there you get this differential algebra for the first diagonal, and something similar happened due to this theorem of structure for the other diagonals. That's kind of the proof. Well.
Thank you very much. Is there any question?
In your main result, why the dependence of n is with the polynomial and not in the degree of the polynomial? And the same question for gamma, why the dependence is in gamma and not in the generic loop into fiber of gamma or f?
Repeat the second question, please.
¿Por qué tu spota n depende del polinomio y no solo del grado del polinomio?
Ajá. ¿Y la otra?
Miras a una gama y eso hace que dependa la n y no la gama genérica en la homología de la fibra.
La gama genérica.
O sea, no es claro qué significa n que depende de f gamma y k.
Okay, let me think about it. Okay. Somehow, okay, this in the proof. Okay. Yeah, actually, the dependence of the gamma it is more related with the orbit under monodromy, and this is because we are defining functions in this, for these ideals in terms of the commutators that you get in the orbit under monodromy. So it is this.
Take this again, for example, if you have a Morse polynomial with
Yes. Okay. The general.
The number of points and infinite is on the monodromy.
Yes. Yes. So for example.
Parasitic, and there is only one gamma.
Exactly.
Essentially.
Yes. I actually in the generic case this. Yeah. It has to do with it. I mean, for example, in the generic case for any k, this gamma coincides with k. So. Sí.
I think the answer to your question is that we are essentially interested in non-generic So F is non-generic. If F is generic,
You
then
generate
it's
everything.
not very interesting. So I'm not speaking about generic fiber, but generic F. So if you have F which is highly non-generic, then you get precisely this N varies. It is not, we have several examples, and so this N varies in the generic case, you get something not very interesting. And then if you have less generic cases, then this N is different.
Sí, I only have time to give some example, but if you increase the genericity, and you get a difference with this N, so in that way it's depending also on the information of F. And also on the orbit, because in the generic case you generate everything, it's a term given by Yelchenko, but it's not generic, then the orbit is smaller, and this number can change.
At the beginning of section 2.2, you write that if the integral is identically 0, then the form omega may be represented in this way. And it seems, this is the Gavrilov theorem, and it seems to me that this is true only in case when F is generic, so-called ultramorphs. If it is not, then the statement is wrong.
No, but this is local. That is if we require E1 and R1 polynomials, but there are just analytic functions. Actually, I wanted to give a sketch of the proof, but I think I didn't have enough time. You define this R1 by integration. You start with this foliated neighborhood, and you connect with this transversal, and you connect any point in this neighborhood with a path, LP, and you define R1 of P by integrating along this path your form omega. And since only in this neighborhood, this is well defined because you are assuming that along these ovals, this integral vanishes, so it doesn't depend if you're going this way or that way. It's well-defined analytic function in this neighborhood. And so it is an analytic function. And by definition, this differential will vanish along these ovals, which means that this difference is a multiple of dx, but only on this annulus. If you require, I'm not saying that they are polynomials. Actually, most probably they are not polynomials because they are given also by integration of this Gelfand-Herrera derivative. But this is just in the local settings. In this,
so these are not polynomials, but
no,
are analytic functions.
Analytic
Yes.
function in this annulus.
More questions? No? If not, I want to thank Jessie, especially for the challenge to talk about this very work.
As I told you, it was proved yesterday. We finished, and I prepared this talk yesterday.
Thank you very much.